is a B tree has a special type of node called a map node, which once again it contains a bitmap to indicate which nodes within that B tree have been allocated. There is nothing that says the number of map nodes has to be exactly the right number to hold a bitmap that fits the entire tree. You can extend the number of maps, you can add new map nodes, and use those maps for data storage. Right? So you can add map nodes at the end of the linked list, and they're not going to be accessed by the kernel because they would indicate bits, or basically they would indicate nodes that go beyond the end of the file. So they're outside the scope of that B tree. Nothing to worry about. This is very, very easy to implement, but for some reason my code doesn't work. So this demo gets skipped. No complaints there, right? Okay. Next up, there's actually, as I mentioned, there's free space inside nodes. You can actually do data storage inside that free space. Once again, my code doesn't work. So we're going to skip this demo. But what I can show you is how it mostly works up until the point that it gets written to disk, when it stops working. Which, it drove me nuts. I've spent an hour working on it, and it gets all the way, at the very, very lowest layer I have, I can see the buffers that are supposedly getting written to disk, and they contain all the data. And then when I read it back in, the data is gone. So I'm going to lodge a complaint with Apple saying that there's something wrong with their disk driver that erases my data hiding attack before it gets down to the disk. I'm pretty sure that's the only possible explanation at this point. So let's look at something else. We're going to look at how we can use Unicode. There's Unicode bugs that we can exploit, and we can actually do data storage inside Unicode strings. Everyone's very excited by this, I can tell. Yay, UTF-16. All right, you people suck. Okay, so what we're going to be looking at is zero-width Unicode glyphs. Basically, a glyph is something that gets displayed to the screen or advances the cursor on the screen. Right? UTF-16 has what are like non-glyph characters. They occupy space within a UTF-16 stream, but they don't display any glyphs when they're printed to the screen, and they don't actually cause the cursor to move. So they're essentially invisible. And we only need two of those. So the first one we have is the null character, which is basically all zeros. And the other one is what we have is the zero width space. It's a space that occupies zero width. Right? Since we've got two, that gives us what? 1 and 0, right? So now we can do data storage by converting our bytes into chunks of Unicode characters, right? So we actually now have a way of converting a stream of bytes into a stream of zero-width Unicode characters. How awesome is that? Very awesome, correct. Okay, so the cool thing about this is mostly what happens is UTF-16 gets converted to UTF-8 on the way back, so it will be read up as UTF-16 off the disk, and then it will get converted to UTF-8 to be displayed on a screen. And the awesome thing is the way that the null character over here gets converted into UTF-8 is it becomes a null terminator, which means your null character actually terminates your UTF-8 string, which means all of the rest of the data is now invisible completely, it gets vanished it vanishes in the conversion process itself, right? So you can actually hide data in a file system by converting your data to invisible UTF-16 characters, appending them to the names of, appending them to file names. So you'll have a file name that's 2 characters plus 200 characters of UTF-16 data. When the forensics investigator comes by trying to look at where all this stuff is, he will read up the file name, convert it to UTF-8, which strips out all of your data, and then start looking inside the contents of that file for your data, when his tool has already basically erased the data for you, right? So it's data that would get printed to the screen. It's incredibly ironic, yes? The data he's looking for is displayed directly in front of him, but it's invisibly displayed. Wow, right? So where can we use UTF-16? Well, there's some cool things, the iPod iTunes database actually uses UTF-16 for everything, right? That means the artist name, the album name, the genre name, the path to the file, basically every single piece of metadata associated with a track inside an iTunes database is stored in UTF-16 characters. And it's duplicated for every single entry. So if you have a track that, like if you've got 13 tracks from the same album, each of them will have the album name individually embedded within that entry. All right? It's also used for file names, for example, in HFS+, in NTFS, and in FAT32, right, in what's called the long file name format. So you can actually do attacks with UTF-16 characters against FAT32 on your phone. Pretty cool stuff, I can tell, right? And obviously, you can do it inside documents. So you can have your document encoded into the UTF-16 character set, and you can do your data storage in there, right? So I call this the ZUU attack, ZWU. We're going to look only at how we can attack an iPod database. Basically, each entry in an iPod database has a maximum of 255 Unicode UTF-16 characters. It takes us 8 characters to encode a single byte, which means that per song, at a maximum, we could encode about 31 bytes. So only looking at like the artist, the album, the track name, and the path, theoretically, we get about 100K of storage per 1,000 tracks in an iPod, which isn't too bad. If you've got a large iPod with a large number of tracks, you can actually have a couple of megs of storage space in there. That's, you know, invisibly embedded. There's some downsides with iPods, like I've been working a lot on iPod attacks. There's also attacks against the structured storage format that they use, the MHBD database. You can do things in there. This code actually does work, except I don't know how to make a terminal display over there. So imagine that I'm executing this from the prompt. I can make it show up one character at a time if that helps anyone. You can pretend I'm typing. Okay, so I've written a module called UTF-Fool. Basically, it only has 2 methods, to Unicode and from Unicode. As you can see here, if we call to Unicode, what we get back is an 88-character length string, which when we print out is 0 width, right? The problem is if you print it directly without encoding it like this, it gets converted, like all of the 0 width space characters get converted into normal space characters, and then it shows up on the screen. So it looks a bit naff. But honestly, it does work. It's one of my few demos that does work. Please believe me. Okay, so like the cool thing is you can attack pretty much anything, including even Unicode. Right? Unicode is itself simply a structured data storage format. Right? So you can fist the Unicode. So next up, we're going to look at how we can move beyond structured format and look at other attacks that we can do. This one's kind of funny because it simply takes a slightly different way of thinking. So we're going to look at browser cookies. Right? First of all, what is a cookie? It's very simple. A cookie is a URL that's been associated with some sort of key, a variable name, and a value. And chances are that value is a base 64 encoded chunk of encrypted binary data that's been sent to you by the website. Right? Well, what do we want to store? We want to store a base 64 chunk of encrypted binary data. Anyone having an aha moment? Yes? Right, no. Okay, so the idea is that you can actually use your cookies file for hidden data storage because you can create fake cookies that contain nothing but your base 64 encrypted data. Right? So looking just quickly at the Mozilla's cookie file, it's an SQLite database. You can access it using only the SQLite 3 tool. The schema is very simple. It looks like this. Basically, the only ones that you need to worry about are the name, the value, the host sometimes, and the ID, which should be incremented anyway. So I'll now show you, yet again, another awesome demo on how we can do data storage. This is guaranteed to be ignored by just about any forensics investigator. You create your data storage, you put it in under lolitapictures.com, and you're away. You guys suck as an audience. No, all right, from now on, 2-drink minimum. Okay, so like rather than storing our stuff inside the cookies file, which is a bit lame, Oh yeah, one of the other things that you can do, right, I forgot to put this slide in here, but basically you can take the Mozilla cookies file and you can create your own table. And then you can do your data storage directly in that table, right? So you can do create table, my hidden secret data, you know, with a text value, and then put your stuff in there. When a forensics tool comes along, what they're going to do is they're going to open that up, they're going to go to the Moz cookies table and dump all of the data out of the Moz cookies table and then close it. Right? They're not going to look at all of the tables that have been defined for that particular database because the people who implement these tools are fucking stupid. So we can do really, really simple things like that, and we're going to get away with it. But let's do something cooler. So what we're going to look at is the SQLite file format. SQLite, once again, structured data storage. All SQLite does is it takes a file, it divides that file up into pages. A page contains a header on the very first page. Then there's all of these free pages which are not allocated. They're stored in a, actually it's not a linked list, it's a binary tree, once again. So, but basically, all of the free pages are stored in a tree, and you can store your data inside those free pages, which we will do. And I actually have a working demo for this one, so like, you guys can relax, calm down, it's all good. Basically, there's more exciting things that you can do inside the page contents. Inside that, it's called a cell, right? Those are what are used to create the binary trees for the tables. Unfortunately, that code is very, very complicated and ugly, so it's not working properly. Unlike all my other much clean code that is also not working properly. But SQLite is really ugly inside. Okay, so SQLite actually, if you have a table in SQLite and it grows very big, SQLite will allocate additional blocks. It will expand the size of that file. If you then drop that table or shrink the size, SQLite doesn't release those blocks back to the system. It keeps the same large size. So what that allows you to do is take an SQLite database, make it very big, drop the table, and then use all of that free space for data storage. All right? So the one problem with that is if auto vacuum is enabled, it can cause your internal databases to be adjusted. And that means when the B trees get rebalanced, all of your stuff gets wiped out. So don't do it on live databases. That's bad. All right, I have a demo. All right, let me see if I can make it work. Oh, uh-oh. Where's my fucking pointer? All right, I can't find the pointer. No demo, I'm sorry. There we go. All right. As you can see, I'm very much prepared for this stuff. Okay. All right, there should be some setting to like mirror stuff, but whatever. Okay, so here's my like really awesome terminal, and what we're going to do is run Python, squeeze, and try and remember the command line options that it takes. Okay, projects, anti-forensics, SQL. Lite, yes. Cookies DB, etc password. So what this is going to do is erase my etc password file, overwrite a portion of my disk, and crash horribly. Or not. Okay, so in theory now what we have is a cookies.sqlite file, which has my etc password stored inside. And we can probably do strings and see if I've been going to naughty sites. Projects, anti-forensics, SQLite, cookies. Oh, that doesn't look right. All right, there's all of that stuff. You know what? I just remembered, I'm an idiot. Okay, so what happened is rather than modifying the existing database, I create a new database called test.sqlite, which you can see here.